Okay, hi. I hope that you're still with me. I just had trouble with my Hangout because I cannot stop. I don't know where to locate the stop broadcast, and at the same time, I don't have a pen. I don't know with the Google Slides I was using a while ago. I didn't have a pen, so I would want to to proceed, but I need to stop it because I need to find a way to be able to write the solutions that I have prepared for the problems that I will be giving to you. So again, I hope you're still with me and you can still um, hang out with me in Google Hangout. Again, for those who are with me right now, can you please um, tell me if you see the 5 problems I have on screen? Again, please chat with me if you can see the the screen where you see the problems. Please leave a comment again. Please, can I just ask a favor? Please help me. Tell me if you can see the problems. I can proceed if you don't tell me if you can see what I have on screen. Okay. Again, please tell me if you can see what I have on screen. Wait, I'm still looking for the chat. Okay, there. Thank you. So we can see it. I just reduced the problem to 7. I mean, from 7 to 5 because there are some important matters I need to attend to in a while. So let me just discuss to you again these 5 problems. So these 5 problems we need be able to be able to know how to approach them by figuring out what gas law it is. So first step is when you read a problem, take note that you need to analyze and read thoroughly the problem and what you're given, what variables you're given, so as to lead you to what is the gas law that you're gonna use. And the moment you figure out the right gas law, then you would be able to recall the correct mathematical equation of that law. Okay, so again, the technique is read and analyze the problem thoroughly and identify the variables you're given. And from what you have identified, you can already figure out what's the right mathematical equation about that gas law that you need to use. When you are identifying the given, please make sure that you do it right. And there's a technique. If you're able to if you're able to watch all the past videos about all the gas law problems, there's a way in order to organize the given so that you won't get confused and you won't um, substitute the wrong values in it. So, are we ready? Only Jean is commenting. For those who are watching, can you please chat for this video and tell me if you are ready to solve the 5 problems with me. Please leave a comment if you're ready. Let us start with problem number 1. That's the first problem I gave to you a while ago. So let's start with problem number 1. Hi, Rhoda. Can you please tell others that we're online so that they would be able to ask me questions about this problem? Okay. So I think we're good and we can start with problem number 1. Okay. So problem number 1. An unknown gas has a, thank you, Miggy. So we're ready. An unknown gas, so unknown gas, I think you're familiar with this. Unknown gas, when we talk about unknown gas, it's always designated as X. Okay? Has a rate of effusion. It has a rate of effusion. Sorry, keep on moving this. So it has a rate of effusion that is 1.93 times that of chlorine gas. And then at the same temperature, calculate the molar mass of the unknown gas. So let's start with the given of this problem. So for problem number 1, it's obvious that our problem is about Graham's law of effusion, because effusion word is being given here, correct? Okay, so the given is the rate. When you say rate, it's always symbolized as V, the rate of an unknown gas, so that is X because it's unknown. The rate of an unknown gas is equal to 1.93 times that of chlorine gas. So that of the rate of chlorine gas. Since chlorine is diatomic, that is Cl2. Now, remember this was the technique we employed in the previous video about Graham's law. Transform the phrase, the statement, as a chemical equation. So we know that we need to put all the V's on the other side so we can put the molar mass expression on the right side, because rate of effusion is very much related to the molar mass. So we can now say Vx over, just divide both sides by the rate of Cl2, is equal to 1.93, in which Vx over VCl2 is equal to the expression of molar mass, which is the inverse. So that is the square root of the molar mass of Cl2 over the molar mass of the unknown gas X. Okay, are you still with me? And since we are to calculate for the molar mass, it's the mm. We don't care anymore about this. About that as 1.93. That's the ratio. We care about getting the molar mass of X here, kani. And we know Cl2. Going to the periodic table, we can already identify the molar mass of Cl2. So let's derive the equation for this particular problem. So we can square both sides first before we can get mm of X, because there's a square root. So by squaring both sides, the square root's going to be removed. And this will now become, I'll just put mm expression on the left, switching it with 1.93. So that's going to be molar mass of Cl2 over the molar mass of unknown gas is equal to the square of 1.93. Are you still with me? Okay, so looking at this, if we cross multiply this particular equation to get mm of X, so cross multiplying, that's over 1, you cross multiply that, and then you get mmx, so you need to get rid of 1.93 squared. So mm of X is equal to mm of Cl2 over 1.93 squared. Okay, correct? In which we can go to the periodic table and the molar mass of Cl2 is 70.9 grams per mole over the square of 1.93. Okay, I hope you don't have any questions so far. Please don't hesitate to leave a comment if ever you have some questions. Like, Madam, where does 70.9 come from? It came from the periodic table. Look at chlorine and times it by 2, because chlorine has a molar mass. Each chlorine has a molar mass of 35.45. And because it's diatomic, it's part of the 7 diatomic molecules. So we would get 70.9 grams per mole. 1.93 is given. Trace it. Trace it from the very first step of this problem. So get ready with your calculator and input the final expression for this problem solving. 70.9 divided by 1.93 squared. And hopefully, I hope you're inputting that right now with me. Hopefully, you will get the answer of the molar mass of that unknown gas to be 19.03 grams per mole. So let me highlight that. And this is the final molar mass of the unknown gas. Now, how do we check again for Graham if our answer makes sense? Remember the concept of Graham. The lighter the gas, the faster it moves. Because in the given here, it says that X moves 1.93 times as chlorine gas. 1.93 is obviously more than 1. That means we would expect that X travels faster than chlorine gas. So if it travels faster, that means it should be lighter than Cl2. Am I correct? So X should be lighter than Cl2. That means, as what we got in this problem, 19 is lower than 70.9. So that our answer makes sense. Okay. Any questions so far? Any questions so far? Please, I will pause for a while, and you may pause this video if you want to give you time to take note of this particular problem. Let me just erase this. Let me just undo this so we can proceed to the next problem. Again, I hope you're taking notes of the answers to this problem and how we approach it. So this problem number 1, it's about Graham's law of effusion because it talks about the rate of effusion and calculating for the molar mass. Okay, so we're good. And we're ready to proceed to our second problem. Let me erase that. Okay. Okay, let me just move this up. Now into problem number 2. Okay, problem number 2. Are we ready? For those who are with me, I hope we're ready to tackle up problem number 2. Okay, problem number 2. Okay, let's read this. Gas X has a molar mass of 72 grams per mole. And gas Y has a molar mass of 2 grams per mole. How much faster or slower does gas Y effuse from a small opening than gas X at the same temperature? So, obviously, there's molar mass, there's effuse word. So this is the type of problem that talks about Graham's law of effusion. So it's more or less the same with number 1. Now, how do we write down the expression for this particular problem? Let's start with the given so that we won't get confused. So we're given molar mass of X, which is equal to 72 grams per mole. And then we're given the molar mass of gas Y, which is 2 grams per mole. It says how much faster or slower does gas Y effuse from a small opening than gas X. So we may either put X above or Y, then we can just compare it. Either of that, you may get the same expression. So since X is given first in the problem, I will just put it in the numerator for the V, because faster and slower depicts the rate. So that's going to be V of X over the V of Y is equal to the square root of molar mass of Y over molar mass of X. Remember, we got this from Graham's law. Graham's law expression is AB, then B over A. That's the reverse of molar mass. But since it's given in the problem about X and Y, so you use X and Y for the subscript. Okay, so this is because we are given molar masses, so we can substitute right away. So Vx over Vy is equal to the molar mass of Y is 2 grams per mole over molar mass of X, which is 72 grams per mole. In that case, you cancel out the grams over mole unit, so because the ratio is always unitless. So please input in your calculator right now. Divide 2 over 72 equals, and then don't forget the square root. There's always a square root if it's Graham's law. Okay, did you input it? And so you're gonna get the answer to be Vx over Vy is equal to 0.17. That's the rate. Okay, so when we cross multiply that to get a statement from this is going to be Vx times 1 is Vx, and so 0.17 is partnered with the Vy. Okay, what does this mean? It means that gas X effuses 0.17 times that of gas Y. The rate is less than 1. That means we expect X to be heavier than gas Y, which is correct in the given. X is 72 compared to Y, which is just 2 grams per mole. So we would expect if we compare X to the Y, X should travel slower, so the rate has to be less than 1. If you reverse the expression, if you want to get the Y's rate, so it's going to be Vy over Vx. If you reverse it, is equal to the square root of molar mass of X over molar mass of Y. Then, substituting it, it's going to be square root of 72 na over 2, canceling out grams per mole. So you would get Vy over Vx to be equal to 6. So in that case, it's the reverse. Vy travels 6 times faster than Vx. So see the difference of the two. Compare these two. Either of that is correct. Either of that is correct basing on the proper substitution of values. Y should travel faster, 6 times faster than X, because Y is so much lighter than X. Correct? Now I'll give you time to absorb this, and please find time to leave a message below this. Okay? Again, kindly broadcast this to the rest of the STEM students who might need help and who needs to know about this. Okay? Please pause this for a while, and you may write this down on your notes about Graham's law while I do erase some of the stuff here. Okay? Let me erase. No comment so far, Miggy, Rhoda, Jean. I hope you're getting this. Let me know if you have some questions, please. Let me know if you have some questions so I can help you. Any questions? Miggy, Rhoda, Jean? Am I too fast? Or is it just fine? Am I too fast, or is it okay with you? Is it okay so far? Thank you, Rhoda, for the quick reply. Okay. Are we ready for problem number 3? Problem number 3 talks about total pressure. Let's read. The total pressure of the gaseous mixture is 1 atmosphere. The mixture of N2 and O2 is known to contain 0.05 mole N2 gas that has a temperature of 298 Kelvin and a volume of 2000 ml. Calculate the partial pressure and the number of moles of O2 gas. Now it's obvious, you have some keywords that will help you identify the right gas law for this. The keyword is obviously partial pressure. So we're talking about Dalton's law of partial pressure. Are you getting it? And it talks about total pressure. So that's about really Dalton's law. So putting in the given, we know the total pressure of the mixture is 1 atmosphere. And if it is Dalton's law, we separate the total from each of the components. We're given the N2's variable, so we need to put it in the separate column for the given. So we're given the amount of moles of N2, which is symbolized by small letter N, always if it's about mole. So that's 0.0500 mole. And then we have the temperature, which is shared by the mixture also, 298 Kelvin. And then the volume of N2 as well, which is just the volume of the container. So it's 2000 ml, and you know that you need to convert your 2000 ml to liters because obviously this is not just about ideal gas law. I mean, this is not just about Dalton's law. You also have to employ ideal gas law because obviously you're given T and V and P and N. So this is the problem in which you can use ideal gas law for the solving of it. And then you are asked to solve for the partial pressure of N2, so that's PN2 question mark. Okay, you're asked for the partial pressure first of N2 and then later on the number of moles of O2. I mean, you're asked for PO2, sorry, but you can't get PO2 without getting PN2 first. Miggy, where did we get 1 atmosphere? Look at the problem here. I'm highlighting it. Are we talking about problem number 3? It says in problem number 3 that the total pressure of the gaseous mixture is 1 atmosphere. It says here. Let me know if you heard me answering your question, Miggy. The 1 atmosphere is given in the problem. I'm pointing at it right now. Okay, did you see it? Miggy? Please answer me if you heard me and if your question is answered before we proceed. Miggy? I'm waiting for your answer, Miggy. Any questions? Any questions, Miggy? None? So PT is 1 atmosphere. Moles of N2, temperature and volume are all also mentioned in the problem. We're asked to get the partial pressure of O2 and the N of O2. But again, we can't get these two without getting PN2 first because N2 is the one that is given. Okay, you can't mix up N2 and O2. Pressure of N2. I hope you know the track here. When we get the pressure of N2, we subtract it from the total pressure, then we would get the partial pressure of O2. Okay? We get the partial pressure of O2 with the moles of O2 using the ideal gas law. Right? I hope you got me. So the first step is to get PN2 using ideal gas law. Ideal gas law again is PV is equal to nRT. Okay, so to get PN2, P of N2, that is just the N of N2 times R times T of the container, which is 2 liters. So let's just substitute our N, our units are okay, right? We got it in liters, Kelvin, mole. So we're good. We may not put it in our substitution. So that is 0.05, 0.0821 times the T of 298 Kelvin, the volume of 2 liters. Okay, so through that, putting all of that, inputting that in the calculator. Sorry, I have to put my equal sign in here beside the over. Okay, so that's gonna be it. Please input that in your calculator. When you input that, the final answer for the partial pressure of N2 is 0.61 atmosphere. That's the default unit of pressure, if you know, because of the R, right? So ATM is the automatic default unit of the partial pressure of N2, in which from here we said that we can get partial pressure of O2 from PN2, in which we know from Dalton's law, let me just use a different color, PT should be equal to the sum of PN2 plus PO2, in which we're getting PO2. So PO2 is equal to PT of PN2. Subtract it. So that's 1.00. Again, we got this from the given, 61. The one we just solved. So you get the PO2, which is equal to 0.39 atmosphere. So this is now our final answer for the P of O2. This Dalton's law says that the total pressure of the mixture is equal to the summation of the individual partial pressure of each gas. Okay. And then we can proceed to getting, we're done with this, we're done with that. We can proceed to getting the N of O2. Let me just erase the given part so I can show to you the solution to get N of O2. Okay, so again, to get N of O2, you need to get or use the one for O2, but you know that volume, for the volume and temperature, it's just the same with N2. So we can just solve readily using, again, this ideal gas law. So N of O2 is equal of O2 times V over RT. Checking the units are compatible, so we can readily substitute that. Pressure 39 and the volume is 2 liters. Real-time board system 0.0821. This happens if the internet is kind of slow, so it limits my live stream. I hope you're me because of that. 298 Kelvin. Okay, so 0.39 times 2 divided by the product of R, 0.0821 times 298 Kelvin. So we would get our final answer of the moles of O2 to be 0.03 in 2 decimal places, mole of O2. Okay, so we were able, the final answer for problem number 3, getting the partial pressure of O2 and the N, number of moles of O2. Okay, on this live stream with me. So again, take this, make sure that you understand, and if you don't understand in below, I can answer it as much as possible. Okay, let me erase my solution to problem number 3, proceed to problem number 4. We're ready to do problem number 4. And so let's read problem number 4 here. Okay. So it says yeah, a finer has a temperature change in 4 times more than the initial. What is the size of the container after the temperature change? Okay. Can you? I hope that you can still hear me. Okay, can you still hear me? Can you still see my screen? It's okay, Miggy. Can you still see the problem on the screen? Please reply if you see problem number 4 here. Problem 4. Okay, we're in problem number 4 now. This is problem number 4. You have a 5-liter container of gas. Thank you, Mel. Welcome, Mel. Thank you for joining. A 5-liter container of gas has a temperature change such that the final temperature is 4 times more than the initial. What is the size of the container after the temperature change? So in this problem, there are 2 variables mentioned. 5 liter being the volume and temperature, T. V and T only. What are we talking about if it's about volume and temperature? You got that right. I hope you answered Charles's / Gay-Lussac's law. Yes, it's correct because it's about volume and temperature. So that's at constant pressure and amount. So let me show you the solution for that now. So you have 5-liter container. That means that's your V1, 5.0 liter. And the temperature change such that the final temperature is 4 times more than the initial. So there's no value. And if there's no value, you can just use symbol. So T1, we can just say it's a T. And it says that the final temperature T2 is 4 times that of the initial. So 4T. What will be the new size of that particular container when the temperature change? So you are asked to solve for V2. Are you following? So again, we designate the initial temperature to just be T because we are not given any variable. So as with any algebraic problems, you designate a certain letter to a certain unknown that doesn't have any mathematical value. So we're now ready to solve the problem because Charles's law says that volume and temperature are directly related. So it will give us the expression V1T2 is equal to V2T1. And since we are to get V2, so that's divided by T1. Cancel that out. So V2 is V1T2 over T1. So what's our V1? V1 is 5.0 liters. T2 is 4 times T. And divided by T1, which is just T. And if you've noticed, T gets cancelled out. So you're left with 5 liters times 4. You'll get 20.0 liters. And that is the answer for your V2. That's simple. So do not get discouraged if the problem seems so strange or there's something that's not normal with it. So if you're given like something like this, relationship, rate, just take note that you can use symbols and eventually it will simplify the problem solving. Okay, how do we check? You know that they are directly related. So temperature increases. You would expect that volume too should also increase. So 5 liters, it became 20. Our answer makes sense. Direct relationship, if one variable increases, the other one should also increase. So our answer is correct. Okay. That's it for problem 4. And again, let me remind you, please take note of that so that you'll be able to review that come test day. Okay, let me erase my solutions for problem 4 so we'll be ready for the next problem. Okay. Okay. Okay, we're up for the last problem. Just let me know if you need more help or if you need more problems. I might be able to give you in a while if you need more problems, or maybe in the class. Okay, so we're up for problem number 5. Problem number 5 states that a person is using an oxygen mask, breathing air through the oxygen mask, and the mask has 30% oxygen, so it's not really pure oxygen. What is the partial pressure of oxygen in atmosphere if the oxygen mask has a pressure of 110 kilopascal? So basically, you're just given very few values. You have 33% oxygen and the total pressure of the mask is 110 kilopascal. So you're given PT of 110 kilopascal and you're given percent of O2 in the mask, which is 33%. What is the partial pressure of O2? So obviously this talks about Dalton's law of partial pressure, but if you come to think about it, you have one mask, 33% of the amount is oxygen, which you've known from Dalton's law that amount and pressure are additive for a gaseous mixture. Additive. So whatever is the percentage of the amount of that particular gas can be so much related to also the pressure of that gas in the mixture. So simply for this problem to just get the partial pressure of O2, it's just basically 33% of the total pressure of the mixture. This is just the same way as imagining your mole fraction. To get partial pressure of a certain gas, it's mole fraction times the total pressure. That's what we discussed. And so this time you're not given mole fraction, but you're given the percentage, in which whatever is the percentage of the amount, that can also be related to the percentage of that of pressure. So we can safely just go to this expression right away, which is, in which case 33% is 0.33 times 110 kilopascal. And you will get the answer to be 36.3 kilopascal. And since the problem states that you need to express it in atmosphere, so you need to do the conversion in which you start with kilopascal. 1 kilopascal has 1000 pascal, and then pascal to atmosphere. So there are 101,325 pascal, which you should put down in 1 atmosphere so that the units will cancel out. I hope that you bear in mind what are the values of your conversion factors so that you will find it easy to convert. You may just convert it right away in the periodic, I mean in your calculator, so that you can get the answer fast and accurate. So putting all that in the calculator, you would get the final answer in 2 decimal places, 0.36 atmosphere. So that is the partial pressure of O2. Okay, so we're able to solve problem number 5. That's the end of it. Again, take note of that, and you may share that with your classmates who need help. Always remember that we have a responsibility to teach others whatever we have learned. Okay? So that's it for now. I cannot give you all the different types of problems for all the 8 gas laws. I'm just giving you an overview of the possible setup. If you're given all these types of problems, how will I be able to figure out what law? How will I be able to identify the correct equation? I hope that I am able to assist you with that. And again, it always begins with understanding every concept, and then the equation must follow after the concept. Okay? Because the concepts will guide you through the analysis and the approach or strategies in solving the problem correctly. So I hope, my dear students, I am able to reach out to you in the best way I can. again, I just can't give you many problems for today. I have limited time. So if you have further questions, please leave it in the comment section below if we can't have time when you meet me personally. Okay? Please, again, it's my pleasure to be able to do this with you. And sorry for having a second take for this live stream because I need to figure out some troubleshooting troubleshooting techniques for Hangouts on Air because I'm using the Hangouts on Air. I can't afford to purchase some encoders for this live streaming. Okay, that's it for now. Thank you so much and have a good rest. Let's all rest and be ready for the week ahead. God bless you. Again, never stop learning, relearning, and unlearning. And always remember that we are loved, we're constantly loved, and we bless others through that love. God bless us all. Bye for now.